topic of this chapter is on orthogonal basis and Gram-Schmidt. How do we orthogonalize independent vectors? So orthogonal basis and Gram-Schmidt. So in an orthogonal basis, every vector is orthogonal to every other vector. Coordinate axes are mutually orthogonal. So this is the case when we have I, J, and K. So you have I here, maybe you make it unit vector. This is K, and this is J. So if you have some vector 3I plus 4J plus 5K, you know how to represent that vector. And if somebody asks you what is the component of this vector x along I, all you do is you take the dot product of x and I, and then you say this is 3. The component along j is x dot j, which is 4, and x dot k, which is 5. So there is 3 here, 4 here, and 5 here. So this is how, and then you add them together, and this is how you get a vector. If you consider your room, then there's this vector is in space, 3 units along x-axis, 4 units along y-axis, and 5 units along the z-axis. So whenever you have orthogonal coordinate system, it's much easier to find the component of or the projections of the vector along each of the coordinate axes. So that is the rationale, or that's the motivation why we want to study this. Why we want to study this section, because the coordinate axes are mutually orthogonal. We divide each vector by its length to make it a unit vector. And changes an orthogonal basis. So this changes. So these are mutually orthogonal. When you divide each vector by its length, so this makes it a unit vector. So now we go from orthogonal to orthonormal. So changes. So this implies. So this step implies changes an orthogonal basis to an orthonormal, which is orthogonal and normalized orthonormal basis and of Q's. So we have these vectors which we called Q, which will be orthogonal, the orthogonal counterpart of the other vectors. So let's see. So vectors Q1, Q2, Qn are orthonormal. This implies are orthonormal if Q transpose I, Q transpose I, Q transpose A, which is actually Qi dot Qj equals 1 for I equals j and 0 else. So this means orthogonal. and this means normalized. Okay. So a matrix with these columns, a matrix with orthonormal columns, is called, matrix with orthonormal columns is called Q. So standard basis in 2D are E1 1 0 and E2 0 1, and these are the columns of a 2 by 2 identity matrix. In n dimensional E1 is 1 0 0 0, E2 is 0 1 0 0, and En is 0 0 1. These are columns of an n by n identity matrix. Obviously, these are not the only orthogonal bases. These are not the only orthogonal basis. We can rotate axes without changing the angle between them, without changing the between them. This implies rotation matrices are examples of Q. So the Gram-Schmidt procedure, orthogonalization converts a skewed set of axes into a perpendicular set, set. Okay. So what are orthogonal matrices? If Q is square or rectangular, and has orthonormal columns and has orthonormal columns, then Q transpose Q equals I. And why is this? Because this is Q1 transpose, Q2 transpose, Qn transpose into, so this is Q transpose, this is Q1, this is Qn, this is Q, and this is, so this row, when dot product or with this column, this will give me a 1, This one with all others will give me 0 because these are orthogonal columns, and this will I will get an identity matrix over here. I'll get an identity matrix over here. And what is an orthogonal matrix? An orthogonal matrix is a square matrix. An orthogonal matrix is a square matrix. Is a square matrix. Is a square matrix. So it's a square matrix with orthonormal columns. Orthogonal matrix is a square matrix with orthonormal columns. So this implies Q transpose equals Q inverse. And if Q is rectangular, and Q transpose Q is equal to I, then Q transpose is the left inverse, Let's look at an example. If Q is equal to cosine theta, sine theta, minus sine theta, cosine theta, this implies Q transpose is equal to Q inverse equals, this is a rotation matrix, cosine theta minus sine theta, sine theta, cosine theta. This is the rotation matrix. It's not a rotation matrix, this is a rotation matrix. This is a rotation matrix. This rotation matrix rotates every vector by theta, and this rotates back every vector by minus theta. What about a permutation matrix? A permutation matrix is an orthogonal matrix. P is 0, 1, 0, 0, 0, 1, 1, 0, 0. The permutation matrix has ones in each column row. So recall, permutation matrix has ones in each column row, and this implies P transpose, these are all orthonormal columns, so P transpose is equal to P inverse is equal to 0, 1, 0, 0, 0, 1, 1, 0, 0. So if I multiply the two, so first I am picking the third row here from this one. From this one I am picking the first row, and from here I am picking the middle row, which is this one. So when I do P transpose P, I'll get an identity matrix. So you can check. If P transpose P is an identity matrix. Okay. Is there another example? No. So there is no other example. So let's define another. I have another property. So a property shared by rotations and deflections reflections, but not by projections, but not by projections, but not by projections. And projections are neither invertible, neither orthogonal, nor invertible. Is that orthogonal matrices preserve the length, preserve the length, whereas projections, they reduce the length, So how do we do that? So because q times x is simply qx transpose into qx, which is equal to x transpose into q transpose into q into x, which this is I. So this is simply equal to x, and this is true for all x. Inner products and angles are also preserved, Why? Because qx transpose into qy equals x transpose q transpose q into y. This is again I. So this is equal to x transpose y, which is equal to x dot y. And this is what I told you in the beginning of the lecture. If you have a vector which is representing, which is in terms of the orthogonal or orthonormalized coordinate x's, then you can simply find the component of the vector along the x, y, and z axis by simply projecting it onto the x, y, or z separately. And the mathematics behind that statement is, if we have a basis, then any vector is a combination of, this is called spanning, is a combination of basis vector. This is the definition of spanning. Okay. So this implies B vector is some x1 into q1 plus x2 into q2 plus xn into qn. Now q1 transpose into B is simply equal to x1 into q1 transpose into q1, because qi dot qj equals 1 for I equals j and 0 x. Okay, if this is true, this implies x1 is simply q1 transpose B, which is equal to B transpose q1. Okay, and similarly B equals q1 transpose into B in the direction of q1. So you project B in the q1. So this is the projection projection of B onto Q1 in the direction of Q1 plus Q2 transpose into B into Q2. This is the projection of B onto Q2 plus so on and so forth plus Qn transpose B into Qn. Okay, or I can write or Q times X. So this one is simply, this is simply Q times X is equal to B. Why? Because this is Q1, this is Qn, this is X1, this is Xn, and this is B. So X1 multiplied by the first column here, X1 Q1 plus X2 Q2 plus Xn Bn, or Qx is equal to B, or if I multiply Q transpose here, I multiply Q transpose here, so I have Q transpose Q X equals Q transpose B. This, by the way, is identity, so this implies X is simply Q transpose B. X is simply Q transpose B, which simply means, which is equal to Q1 transpose Qn transpose B, and this is equal to Q1 transpose B Qn transpose B. Also note, from here this implies B norm is equal to Qx norm, which is simply equal to the X norm because the length is preserved. Because length is preserved. But X norm from here is Q transpose B squared. It is the Q transpose B norm, and the Q transpose B norm is simply Q1 transpose B square plus Q2 transpose B square plus Qn transpose B square. Right? Okay. Now Q times Q transpose equal I implies inner product of rows of Q and Q transpose Q equals I implies inner product of columns of Q. This implies rows of a square matrix are orthonormal whenever the columns are, and one such example is, for example, Q equals 1 by root 3, 1 by root 3, 1 by root 3, 1 by root 2, 0 minus 1 by root 2, 1 by root 6, minus 2 by root 6, and 1 by root 6. And you see all columns and rows. So columns and rows are orthonormal. So columns, you can check columns and rows are orthonormal. Okay. What happens if you have a rectangular matrix? If you have a rectangular Q, so rectangular matrices with orthonormal columns, with orthonormal columns. So Qx equals B. Q is m by n. Q is m by n with m greater than n, and these are n orthogonal vectors Qi are columns of Q. Okay. So if you find a least square solution, so let's find a least square solution. So find a least square solution. So the least square solution is Q of x equals B. Q of x equals B, or Q transpose Qx equals Q transpose B, or x equals this is identity, or maybe right. So this is identity, or x hat equals Q transpose B, or P, which is equal to Q x hat equals Q times Q transpose B equals P times P, where P is QQ transpose. Okay. Or we can prove it another way, or as another way, and that is, we know the projection matrix is actually A into A transpose A whole inverse A transpose. So I write here as Q transpose Q whole inverse Q transpose. This is identity. So this is simply equal to, QQ transpose, which is the same case over here. And this P is, by the way, m by n. So in the rectangular case, projections do not reconstruct B, while in the square case they do. And there's this example over here. So let's look at this example. We have looked at this one before too. So if we project D, which is x, y, z, onto xy plane, this implies P was x, y, and 0. P was x, y, and 0, which is simply the sum of projections on x, y axis, where Q1 is 1, 0, 0, 1, 0, 0, or Q1 transpose B is simply x, and Q2 is 0, 1, 0, or Q2 transpose B is simply y, and P is Q1 transpose plus Q2 transpose, which is equal to 1 0 0 0 1 0 0 0 0, and p times x y z is simply x y 0. So projections onto a plane, so this implies projections onto a plane is equal to sum of projections onto q1 and q2. So if you consider this example, so maybe this one is probably easier. So this is what this is saying. If you have this vector x is equal to 3i hat plus 4j hat plus 5k hat. So x dot I hat is equal to 3, which is this q1 tb. X dot j hat equals 4, and x dot k hat equals 5. So this is what this section is telling you. If you want to find the projections, yes, if these are orthonormal vectors, the coordinate axes are orthonormal, then you simply take the projections of x in the direction that you want, and you'll get simply, you can read them off from these vectors, the coefficients of these unit vectors. So orthogonal matrices do introduce no instability, introduce no instability because lengths remain same, and round off is under control. So these are very important matrices that we would like to work with. Okay, so the next topic in this section is the Gram-Schmidt process. The Gram-Schmidt process, and this process is how we orthogonalize independent vectors. So this process is simply telling you how to orthonormalize a set of independent vectors. Okay, so given A, B, and C are independent vectors, how do you compute their orthonormal counterparts, say Q1, Q2, and Q3. So there's no problem with picking the first one. No problem with Q1 because A or B or C, it's up to you which one to pick, can go because A can go in the direction of Q1. Okay, so let me draw a picture. So we have, or maybe I'll draw it over here. So we have A over here. So what he's saying is, you say Q1 is vector A and you normalize A by its length. If you do that, because Q1 transpose into Q1 is A transpose into A over A magnitude square, which is norm square, which is equal to A norm square over A norm square, and this is equal to 1. So this is normalized. So this is the first one. So pick either one, A, B, or C, or D, or E, and then you draw this one. And then suppose you have B over here. So this is B. So what you do is, so to find this next, so to find Q2, what you do is project B onto A. Project B onto A. This one is, so when you normalize this one, this becomes Q1. So A, or this one is Q1, and this one would be B dot Q1. So this is this projection length, and this is in the direction of Q1. So this component, the error vector as before for when we were doing projection, this is B minus B dot Q1 in the direction of Q1. So this would be orthogonal to this one, and obviously this will contribute to Q2. So if Q2 is in this direction, if Q2 is in this direction, then obviously this one is in the direction of Q2. So B vector is simply B vector, and from the B vector you subtract the projection in the direction that is already settled. If you do that, now you can check. So check what is B dot Q2. So B dot Q2 is simply B dot Q1, I'm sorry. Whether B and Q1 are orthogonal or not. So B dot Q1 minus B transpose into Q1 dot Q1. So Q1 dot Q1 is 1 because it's normalized. So this is equal to simply B transpose Q1 B transpose Q1 minus B transpose Q1, which is equal to 0. Or Q2 is simply B vector divided by the norm of B. So this is how you get the second vector. You simply subtract. So this is the projection of B onto the direction that has been fixed. And this is in that direction. So obviously, maybe I go here like. So projection of B onto the direction that has been fixed, and if you subtract it, obviously there is no component. So this B has no component along Q1. There is no component along Q1. Okay. And how do we find C? And similarly, C vector is C minus C transpose into the direction that has been fixed in this direction minus C transpose into the direction that has been fixed, Q2 in the direction Q2. And obviously Q3 is simply the C vector divided by its length, and this will give me the third component, C. Okay. So subtract from every new vector. So the process is this as simple as that. So subtract from every new vector, the direct from every new vector its components in the directions that are already settled. Okay, so let's do an example so that we know what we are talking about. So A is 101, B is 100, and C is 210. So if you want to check, A is independent of B is independent of C, all you need to do is, this implies find X such that AX equals 0 and X equals 0 is the only solution, Okay, and you can go home and check whether this is true or not. So if it has a full set of pivots, obviously this has linearly independent columns. Okay, so Q1 is A vector divided by the length of A, which is equal to, the length of A is 1 over 1 square plus 0 square plus 1 square under root. This is the length of A, and which is actually equal to A transpose A square root. Okay, and then this is this vector over here, 101. So this is 1 plus 1, 2. So this is 1 over under root 2, 101. And you can check Q1 norm is actually 1. So you can check this is 1. So this is normalized. What about B? So B is B minus B transpose into Q1 in the direction of Q1. So this is 100, 100 minus B transpose into Q1 is simply 1 over root 2. So B transpose into Q1 is simply B dot Q1. So B transpose into Q1 is simply B dot Q1. So this is 1 over under root 2, 1 over under root 2 in the direction of Q1. In the direction of Q1 is 1 over root 2 into 101, and this is equal to 100 minus half 0 half, and this is equal to half 0 minus half, and the length squared is 1 over 4, or half squared, plus 0 squared plus half squared. So it's 1 by 4, 1 by 4, so it's half. So this implies B, the norm of B is simply 1 over root 2. And if I do that, so what is Q2? So Q2 is B divided by the norm of B, which is equal to 1 over under root 2. So this under root 2 goes here, and I have half outside, and I have 1, 0, minus 1. This is equal to, cancels with this one, so 1 over under root 2, 1, 0, minus 1. So if I compare this vector with this vector, I see that 1, 0, 1, this is 1, 0, minus 1. So check Q1 dot Q2 is 0. And what about the third one? So C vector is C minus C transpose into Q1 in the direction of Q1 minus C transpose Q2 in the direction of Q2. So this is 210. So 210 minus C transpose Q1. C transpose Q1 is, so Q1 is 101 1 0 1 0 1 0 1, so it's 2 minus 2 over under root 2. So this is C transpose Q1 into 1 over root 2 into 1 0 1 minus C transpose into Q2. C transpose into Q2 is again 2 2 1 0, so it's 2 over root 2 into 1 over root 2 into 1 over root 2 into 1 0 minus 1. So I get 2 cancels with this one, 2 cancels with this one, so I am left with 2 minus 1. So 2 minus 1 minus 1. I have 1 minus 0 minus 0. I have 0 minus 1 and plus 1. So this is equal to 0 1 0, and this implies C's length is already 1, so this implies C Q3 equals C equals 0 1 0. And you can also check, you can check Q1 dot Q3 is equal to 0 and Q2 dot Q3 equal to 0. So now all are orthogonal, and my matrix Q, which implies Q is simply Q1, Q2, Q3, and this is equal to 1 over root 2, 0 minus 1 over root plus 1 over root 2 plus, and then this is minus, and finally 0 1 0. And these, all the rows are orthogonal, all the columns are orthogonal, and this is a square matrix, so this is an orthogonal matrix. This is an orthogonal matrix because Q is square, because Q is square and columns are rows are orthonormal. Okay, so just let me recap. Gram-Schmidt process. Gram-Schmidt process starts with independent vectors A1 to AN, and ends with orthonormal vectors Q1 to Qn. Okay. At step J, it subtracts from AJ its components in the direction Q1 to Qj minus 1 that are already settled. That is, AJ equals AJ minus Q1 transpose A1 into Q1 minus Q2 transpose A2, minus Q2 transpose A2 into AJ. This is AJ. This is AJ. We're talking about AJ. AJ in the direction Q2 minus QJ minus 1 transpose into AJ into QJ minus 1. And then you do QJ is simply AJ divided by the norm of AJ. Right, by the norm of AJ. So AJ minus Q1 transpose AJ, Q1, so this is the direction, this is the projection in the direction of Q1, in the direction of Q1, projection in the direction of Q2, in the direction of Q2, or projection onto Q2 into the direction of Q2, projection of in the direction of Qj minus 1, onto J minus 1 and in the direction of Qj minus 1. So the last topic of this chapter is on factorization. Just like we had A is equal to LU, we can also do factorization. A is equal to QR. A is equal to QR. So we can write A, B, and C, A, B, and C as a combination of QIs, and which is A can be written as A transpose into Q1, A transpose into Q1 in the direction of Q1. B can be written as B transpose into Q1 in the direction of Q1 plus B transpose into Q2 in the direction of Q2, and C as C transpose into Q1 in the direction of Q1 plus C transpose into Q2 in the direction of Q2 plus C transpose into Q3 in the direction of Q3. So B in the direction of Q1, B in the direction of Q2, C in the direction of Q1, C in the direction of Q2, and C in the direction of Q3. If you do that, or A equals A, B, C equals Q1, Q2, Q3 into, so this is Q, and here I have Q1 transpose A, 0, 0. So Q1 transpose A, weighting this column Q1, I get this A, the first column here. Then I have Q1 transpose B, Q2 transpose B, and 0. Finally, Q3 transpose C, Q1 transpose C, Q2 transpose C, and Q3 transpose C. So this whole thing is weighting all these columns, and this gives me this column C over here. Okay. This is called R. This is R, where R is an upper triangular, and it's called R because non-zero entries are to right of main diagonal. Okay, so let's write A in terms of QR for the previous example. So A was 1, 0, 1, 1, 0, 0, 2, 1, 0, and we found q was 1 over root 2, 0, 1 over root 2, 1 over root 2, 0, minus 1 over root 2, 0, 1, 0, and this was under root 2, this was 1 over root 2, this was 1 over root 2, this was 0. And similarly, this was root 2, this was root 2, this was 1. This is actually the length of A. This is the length of norm of B, and this is the length of norm of C. And you can multiply out and see whether this is equal to or not. So this is the important result, every M by N matrix with independent columns can be factored into A equals QR. A equals QR, where columns of Q are orthonormal, and R is upper triangular. R is upper triangular and invertible. So whenever the columns are independent, you will have an upper triangular matrix that is invertible. So with M is equal to N, with M equals N, all matrices are square. All matrices are square, and Q becomes an orthogonal matrix. So what is this going to help us? How is this going to help us? So let's look at the least square problem. So least square problem revisited. Least square problem is revisited. So if we revisit the least square problem, we have AX equals B. Now we have QRX equals B. QRX equals B. Maybe later on. So ARX equal to B implies A transpose A, X equals A transpose B. Okay. And what is A transpose A? This is QR transpose into QR into X equals QR transpose B. So this becomes R transpose Q into R into X equals R transpose Q transpose B. Q transpose Q is I, whether Q is rectangular or square doesn't make a difference. So this implies R transpose R X, R transpose R X. So this is X hat actually. This is X hat. So R transpose R X hat is equal to R transpose Q transpose B, or this implies R X hat equals Q transpose B. So instead of solving QRX equals B, we solve Rx hat equals Q transpose B, and since this is upper triangular, Since this is upper triangular, this implies we can do it by only back substitution. Only back substitution. Only back substitution is required. Okay. So same concept of orthogonality applies to functions. So same idea of orthogonality applies to functions, which implies sines, cosines are orthogonal. Since sines and cosines are orthogonal, this implies fx can be written fx can be written as a combination of sines and cosines, which is actually what is done in the Fourier series. So this is what the Fourier series does. It breaks up the signal into its sines and cosines. So we can always write a function as a sum of orthogonal functions. Any function has there's some restrictions, but as far as electrical engineering is concerned, all functions all functions which can be generated in the lab can be written as a sum of cosines and sines. So this is all we want to talk about in chapter 3. So determinants you need to cover yourself. You have already looked at determinants in your high school, and I don't think so I need to spend time on the determinants. All you need to get from that chapter is how to compute a determinant, what are the properties of the determinant, and which I think you already know. So I don't want to spend time on determinants. And this is including the determinants. This is the course for the midterm. Midterm is going to be on campus, and after the midterm, hopefully we'll meet in person, and then we'll solve the second problem in linear algebra, which is ax is equal to lambda x, or the eigenvalue problems. Again, if you have questions, we can discuss on Mondays, or you can email me. Otherwise, you need to do all the questions at the end of each sections. The more you practice, the more would be the more you'll be able to do problems in the midterm, and you'll be more comfortable. You'll be more comfortable doing problems that come in the midterm and the final. Just heads up, the problems that come in the midterm and the final will not be from the end chapter problems, but be from somewhere else. But since you should have done so many, you must have, if you have done so many problems that have been assigned and that are given at the end of the sections, then I don't think so you'll have a problem attempting the midterm or the final. Okay, good luck for the exam, and I'll see you on campus inshallah after the midterm. Thank you.